So, good morning. We start our Monday's lecture. It's continuation of the course of theory of distributions or generalized functions. And we continue to follow the book of Vladimirov. It has advantages and disadvantages. Its main advantage is that it is very fundamental and contains all materials that we need, even more. Disadvantages that it is written in very, very general framework, multidimensional case, distributions not only on the real line or on Rn, but on open sets. And he considers such things that, for example, some function is infinitely differentiable on some open set. And then he considers closure of this open set, so the boundary also of this set, and consider the space of functions which can be continued continuously with all derivatives on this on this closed set, and so on. Our basic example is real line, and who are basic functions or test functions. These are all infinitely differentiable functions, such that there exists interval, bounded interval, and support function is inside this interval. So what is support function? It is closure. It is closure of all points where function is non-zero. So in any event, if support is inside some interval, function is zero outside of this interval. Function is zero outside of this interval. Who are distributions or generalized functions? This is the space of continuous linear functionals on this space D of real line. The main problem is that on this D, it is not easy to define topology on this D. So it is so-called topology of inductive limit, and we shall not do this. But it is easy to define convergence. So this sequence of test functions converge, for example, to zero, if, first of all, there exists such interval, bounded interval, that supports of all these functions are in the same interval. This is very important. So it could not be pictured that support of one function is here, another is larger. So if sequence is convergent in D, in the space of test functions, then there is some interval. Of course, for each sequence, it's its own interval. And all supports are inside this interval. Then on this interval, and this is now finite interval, sequence of derivatives for any derivatives converge uniformly to zero. So this is uniform convergence with all derivatives on closed interval, which is the same for all in this sequence. And then functional is continuous if it's map sequence which converge to zero into zero. Yeah. So then function is continuous. Now we consider the easiest examples of generalized functions. They are called regular generalized function. So take some function which is integrable, and then define this integral and call this define the functional which is defined by this formula. Of course, since phi is always concentrated on bounded segment, it is enough that f is locally integrable or summable, as called Vladimirov. Locally means that it is summable on any finite interval. So we need not that function should be integrable over whole real line. So function can very quickly increase on the real line, yeah? But on each segment, it is integrable. Then this integral is well defined. And of course, this is continuous linear functional on the space D. Why? Because we can estimate it by supremum. For example, it can be estimated by supremum of this function and supremum of function phi and supremum of function phi. Yeah. We ask that it is local because local summation implies that function is locally bounded. So each function is locally bounded on each interval. Then it is, of course, interesting question. If we take two different functions, would they define two different functionals, or it can be such functions are not the same, but functionals are the same? It is not the case, and this is the famous lemma, the Dubois-Reymond, and function which is locally summable vanish almost everywhere on this. Roughly speaking, we can tell following: if two function or if function determine functional by this integral, which is 0 for any phi here, then our function is almost everywhere 0. For continuous functions, it means that it is just everywhere 0. So there is one-to-one correspondence between locally summable functions and functionals which are defined by integrals. Yeah, we shall not go into details. Measures. You did not have theory of measure, but it's useful to have this in mind. Yeah. So measure is function, but not of points, but of sets. To any set, for example, volume, area. Yeah. To any set, we can assign number. And the main property of measure is that it is countably additive. If we take union of disjoint set, case important that they disjoint. So, for example, if you take few disjoint bodies, then the volume of unions is the sum of volumes. Yeah. So, for example, the measure can be defined as just integral over interval. So, measure of interval, it is just this integral. Discrete measure, also very important. It is concentrated in countable number of points, hg, and measure of each point is some number. Then measure of set is just the sum of these numbers with respect to all points in this set. So in any event, if you have measure, and Vladimir considered directly complex measures. So measures which take complex values, yeah. Then we can define such numbers, and okay, as any complex number, we can expand it into different parts, and then if measure has different signs, we can expand it into positive part and negative part. And if you have complex measure, it is in fact can be represented as in this way. This is positive real valued measure. This is positive real valued measure I, and again difference of two real valued measures. And if you have measure, then we, in this similar way as for function, we define continuous linear functional on D by integral with respect to this measure. So for example, in the simplest case, it can be just integral phi x dx. Yeah. Again, similar theorem. If two measures coincide, if functional for some measure is 0 for any phi, then measure is 0 measure. So it is again one-to-one correspondence. It cannot be that you have two different measures, and as a result we get the same functional. If functionals are different, measures are also different. Then good definition. For functions, we know the notion of this function is non-negative. And we also know for measure, the notion measure is non-negative. How to define the notion of non-negative distribution or generalized function? Again, through usual functions, ordinary functions. So this is definition. Generalized function is said to be non-negative if integral, if f were usual function, it would be integral. And it's clear that if function phi, basic function non-negative, and this non-negative, integral should be non-negative. But now we don't have integral. F is arbitrarily generalized function. So and we tell that it is non-negative, that for any phi which is non-negative, we have that the application of functional to function is again non-negative. again non-negative. Then in fact it's not so many. Then in fact it's not so the class of non-negative. The class of non-negative distributions is not something new. For generalized function from this space to be non-negative measure is necessary and sufficient to be non-negative. So if you have measure, of course, measure give us non-negative functional, yes? If measure non-negative, of course, non-negative measure, not arbitrary measure, but to be non-negative measure. Some people just define measure as non-negative measure, but in any event, yeah. So if you, but what is more interesting, other way around, if you have non-negative functional, then it's determined, it is determined by measure. Then it's determined by measure. The simplest example of generalized function is delta function. Clearly, that it is because it's less than maximum of function of any interval, that it's in D prime. Then we can tell that D delta x is x for any x non-zero. So and support delta is just 1 point. No, because if you take what is the meaning of support? What is the meaning of the point where delta function is 0? How we define delta function is not function of the point. What is definition that delta function is 0? Definition of delta function in some point is definition of generalized function in some point is 0. It means that if we take some neighborhood of this point and in some neighborhood it's 0, if we for any test function with support in this neighborhood, application to it is 0. So if you take any point which is non-zero, we can take any interval, and then this functional is 0 for any function with support here, beside of this point. Now we want to prove that delta is a singular generalized function. So what does it mean? That there is no usual regular function which is locally integrable, such that we can represent it this way. So let us take phi and multiply to x square. This is multidimensional case. It's not absolute value x square. So it means that it is square of the norm of phi. So in our simple case, it's just x squared. So x squared multiplied by phi, of course, it's also a test function. So we can write in this way. So and this is nothing else than this function applied to phi, and this function is equal to 0 in the sense of generalized functions. Yes, so x squared f is equal to 0 in the sense of generalized function. So, but this is usual function, and we have this lemma of Dubois-Reymond, usual function, which is 0 in the sense of we multiply by this to make 0 in 0. Otherwise, it would be not work. But we know by lemma of Dubois-Reymond that if some regular function is functional is 0, then it is 0 as usual function. So this means that this is 0 as usual function. Now we considered cap function at the beginning, at the previous lecture. So it was function which was some cap, which is going to 0, and it's 0 in the point minus epsilon and epsilon. And so, and it's given by this formula, some constant. The meaning of this constant is such that we want the integral of this function is 1. And here is exponent epsilon. I recommend you to write by hand how it's look. epsilon in the nominator minus epsilon square, in denominator epsilon square minus x absolute value square. So this function is kept. Because no, you should look to this function and think a bit about it, because here is the crucial point. Such this go to 0. This is in fraction, and this is an exponent. Yeah. We want to prove that these functions, kept functions, they have some interesting property, and you can do this. You can simulate this on computer. In fact, it will be a numerical task later on such simulation. You can see that how we imagine a delta function as some spike which goes to infinity, and if we write graphs of these spikes and put epsilon to 0, we also see that they look in the same way. So it supports our idea. It supports our idea. Yeah, what is convergence in the space of generalized function? It means that if we apply this to test function, it should converge to this applied to test function for any test function. Yeah. So we should prove this. We should prove this for any test function from D. Okay, so we subtract from this, subtract from this, and what we use, what we use, such integral of the cap is 1. So just phi 0 is the same as phi 0 multiplied by 1 integral of cap. So we can write in this way. So it is difference of this maximum, and also support of this function, of this cap function, interval minus epsilon epsilon. So we get this integral is 1, and this goes to 0. Yep, this goes to 0. Okay, so cap functions. Okay, and now we would like to go. To a very interesting class of formulas, which are known as Sahotsky formulas. And before we would determine singular generalized function. So this function is neither given by usual function, which is defined as principal value of this integral. So here is singularity. So we cannot just write this integral. What is principal value? It is limit when epsilon goes to 0 at minus infinity to minus epsilon, and here is plus epsilon to infinity, phi x dx. So our aim first is to prove that this formula really is well defined, that this is well defined for any basic function phi, and more that this formula determines continuous linear functional on the space of basic functions. It's no, I don't like presentation as here. It is too short, and it would be very short separate lecture to prove that this is continuous linear functional on the space of test functions.